Hello, my name's Greg Durgin, and my talk today is on space ambient power as a stepping stone for space solar power. Thank the Space Solar Power Workshop once again for having me here to speak, and really appreciate the amazing effort that the organizers of WISEE 2020 have made to make this conference possible, given the crazy circumstances. For this particular work, I'd really also like to thank the many sponsors that have supported our wireless power transfer work over the years. None greater than the Space Solar Power Institute and the William Brown Fellowship at Georgia Tech. Space solar power is an all-or-nothing enterprise. That is, you cannot build half of a space solar power satellite because you need enough aperture not only to gather power in space, but also to have sufficient transmission aperture to get it back down to Earth. And of course, it's our old friend, the diffraction formula, which says that the diameter of the transmitter times the diameter of the receiver have to be on par with the distance r times lambda. Now, a lot of experts have agreed that r really needs to be in geostationary Earth orbit satellite. That's going to put it at least 36,000 kilometers from the nearest point on Earth. That's very far away. And even if we go up to about 5.8 gigahertz, which is just about the most comfortable unlicensed band you can transmit at, and still have decent propagation losses that aren't particularly sensitive to weather and clouds and things like that, as well as the atmospheric absorption lines. That means this is still going to be a significant product. You're going to have to at least put a kilometer in space of diameter and have at least a kilometer on the ground in order to focus energy at 5.8 gigahertz, which has a 0.05 meter wavelength, about 5 centimeters. So launching that much infrastructure into space is really daunting. Even if we had all the engineering worked out, even if we had all the politics worked out, and the economics worked out, and the ground station worked out, it would still be an onerous amount of money to invest in infrastructure, spaceborne infrastructure, that we would need to launch, install, support. And for a prototype system, that's extremely daunting. You can't build half of a space solar power satellite because each extra square footage that you add to the satellite not only increases the power collection and the amount of power transmitted back to Earth, but it also adds coherence to this beam to even get close to this diffraction limit here. Now, this is a problem. And so what we're going to do is propose an incremental stepping stone where we would incur a very tiny fraction of the cost of a space solar power satellite system. In the process, we could do something very useful, something that might even be commercially viable, and still proof a lot of the concepts, like launching a big piece of infrastructure up to geostationary Earth orbit satellite. Now, how are we going to do that? What we propose is building a space ambient power network. What is ambient power? Ambient RF power is power that exists everywhere in your environment due to either intentionally or unintentionally transmitted RF sources. So, what can you do with ambient power? It's going to be a very low level, right? Well, if we look in the world of RFID, an RFID tag will turn on if it receives about -22 dBms of power. That's decibel milliwatts. Translated into watts, that's actually about 6 microwatts. If you can get that out of your antenna into a chip, you can power up the integrated circuit of an RFID, do basic computation, sensing, and even a little bit of communication through the backscatter by using the ambient power reflecting off of the antenna as your communication network. So, if you had some readers around your environment, you could collect all sorts of interesting data from around this environment. Here's a typical city corner. What kind of data could you collect with an ambient power network? Well, you could put sensors in the traffic lights that would intermittently ping and disclose if they've seen an outage in a light bulb. You could put moisture sensors here in the urban plantings of trees and shrubs, extraordinarily low-cost sensors that would absorb power and report intermittently if the soil was too moist for too long. You could have glass break sensors to protect your businesses. You could have crowd noise sensors, occasionally pinging for acoustic noise, reporting if there's crowds gathering and some sort of commotion. You can have paint sensors, parking spot sensors, all sorts of interesting ideas. And of course, the economics of this type of sensor system are very different than the power grid economics. For what you pay for a single AA battery translates actually into, when you compare it to the total storage capacity, hundreds or thousands of dollars per kilowatt hour. Not all energy is made the same. You're paying for portability in that case. And if you didn't need the battery, you could enable all sorts of interesting applications involving ambient power and sensors. Now, let's compare this to an actual space solar power design. When I talk about space solar power, the difference between that and a space ambient power design is that I'm focusing power into a much smaller location because I want to build a rectenna farm that collects that power and ties into the grid. So we go over here and we look at our basic parameters. I've got geostationary Earth orbit. That's my altitude. I'm going to do all of my calculations as if I was in Atlanta, Georgia. Even though we would probably want to put a rectenna farm in a much more rural place. Here's the radius of the Earth. 50 degrees is roughly the elevation that you get in Atlanta. Atlanta is about 33 degrees latitude above the equator. And if you put something in geostationary Earth orbit, that's roughly the angle of altitude or elevation that you need to point towards that source. Anyway, our aggregate distance is about 37,000 kilometers. The max RF intensity that we're going to tolerate on the Earth at our rectenna farm is about 250 watts per meter squared. Very conservative estimate, certainly safe. Space solar intensity, this is a constant. It's going to be about 1.36 kilowatts per meter squared when you're out in outer space. We're going to assume a conversion efficiency of 30%, frequency of 5.85 gigahertz. That's the corresponding wavelength of 5 centimeters. And in order to make this system work, we're going to need about 1,380 something meters of collection aperture diameter to get sunlight. And that is going to beam down to Earth. The total amount transmitted in this system is going to be about 614 megawatts, and we'll be able to collect about 368 megawatts transmitted down to Earth once it's converted into microwave power, and of that we're going to be able to collect about 368 megawatts if we build an extraordinarily efficient system on the surface of the Earth. That's quite a lot of coin. As a rule of thumb, a megawatt provided over a year is about $1 million. 1 mega million. So that's our baseline system. How would this compare to a space ambient power network? So now we're going to start off calculating the exact same parameters. Same orbit, same angles of inclination, same distance to the satellite system. Now look at this. We're only going to try to achieve 0.84 watts per meter squared on the Earth. 800 milliwatts per meter squared. That's all we need to get our power threshold and drive a lot of interesting applications with a little margin to spare. Same space solar intensity, same transmission efficiency, same frequency even. 5 centimeter wavelength. Now our solar collection diameter can be a lot smaller because we're not handling nearly as much power. We're going to make that 330 meters. For our transmitter aperture, we can also make that smaller because we're covering a wider area on the ground. As a result, that's also going to be about 1/3 of a kilometer, much smaller than our power satellite. Now, keep in mind, this is a radius here. The area is only about 1/20th of the previous page's design for a space solar power network. Means that should be about 1/20th the infrastructure cost, 1/20th the launch costs into space. Now on the Earth, we're going to be able to cover 5.7 kilometers of diameter. And that will mean that we will have to collect, if we integrated everything around the urban area, 21 megawatts. Notice only 35 megawatts of power was actually transmitted. That's much lower than if we had wired up infrastructure on Earth. And keep in mind, when we're using a space ambient power satellite, this is not a quote-unquote green source of energy. The greenest thing to do would be to not launch the application. This is one of the greenest possible ways that you could launch this application in terms of powering it. But remember, this is extra insolation that you wouldn't have otherwise had, since you're not replacing an existing power source on Earth. Just something to keep in mind. So the space solar ambient power system is going to be a lot easier to handle and easier to build and cheaper to build. And keep in mind, there's no infrastructure on the Earth. We don't even have to have a rectenna farm. So that eliminates that completely. Now, however, if we wanted to use a space ambient power network to drive sensors and other sorts of things, we would still need to deploy things like collector stations and little sensors, but that would be a much more ad hoc type of environment. So, what does 5.75 kilometers look like on the surface of the Earth? Well, here I've superimposed it on a map of Atlanta. Here's 5.75 kilometers across, and I've actually foreshortened this because remember, this is not coming from directly overhead. This dimension will be longer, more like 7-point-something kilometers. And the area that I've enclosed here is the densest part of the urban area of Atlanta. It has home for several 100,000 people and most of the big businesses that constitute the urban core, including Georgia Tech campus right over here, my old condo, all the downtown restaurants and everything, dozens and dozens and dozens of office buildings all around here, and parks and many other things that you would want to keep an eye on. and take care of with space ambient power. So, in conclusion, ambient power networks are extremely important. So, in conclusion, we talked about what ambient power is and some of the cool things that you can do with an ambient power network. We said that one of the only practical ways to actually provide this network in terms of sheer infrastructure and power usage is through a space-based system. We said that a space-based system would only require about 5% of the infrastructure that a space solar power network would require. Now, there are also some benefits to using a space ambient power network as a stepping stone for space solar power. That is basically, you want to get people used to the idea that a little bit of RF power is raining down from outer space. At 250 kilowatts, 250 watts per meter squared that I outlined in the previous space solar power baseline design, you probably wouldn't even feel that, even if you walked through it, even if you were right in the middle of a remote rectenna farm. This is 3 orders of magnitude less. It would be less specific absorption or total power incident on you than carrying around a handset in your pocket or making a call on a phone or using any other wireless device. And it would get the public used to the idea, which may be its own paper and discussion point. But it would also provide a lower cost way to proof all of the technologies that you would need to do SSP. All the transmission technologies, all the rectification and earth collection type of technologies, all the space-based infrastructure. It would be a really interesting technique. So now I'd like to hear some questions and answer some of your points. Thank you very much.